Why hello lovely humans, Jen Foxbot here. Welcome to another edition of Math Mondays. Da 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 da. Yeah. Alright, in this episode we get to tackle tipping force. Yes. In other words, it's basically the application of torque to figure out how stable or not a certain object is. So we've hopefully all experienced this when we go to sit on a seesaw and our friend is either way bigger or way smaller than us, like this little example. So in this case, you'd probably quickly guess that the seesaw is going to tip in the direction and this person's just going to be sitting on the ground and be like, this is frustrating. But never fear, we actually know how to remedy this. Our bigger friend can just scoot forward so that they are closer to the fulcrum point. And the reason why this works is because of torque. So torque, hopefully, as you remember from the last episode, is just the force, or in this case, the weight of the person, because it's just their mass times the force of gravity, or the acceleration due to gravity, times the lever arm, or the distance from which the person is sitting. So in this case, if we have the larger person scoot forward, their force or their weight is going to be acting at a smaller distance, and we can actually balance the two by adjusting that lever arm. Ta-da! So next time you're at the park, try this. It's usually not the case that you can move the fulcrum point. That also works. So if you just move it closer to the larger person, that would have the same effect as reducing the lever arm, which you could call L or D or what have you. But basically it's just this distance. So this is also really important in athletics like parkour, where you're jumping on or off of objects and you want to make sure that they don't tip over, because that is an unforeseen circumstance that your brain probably didn't calculate ahead of time. And also in general, like as we are using objects, if we sit on a chair, we want to make sure it doesn't tip over, right? That's a good thing. So by understanding tipping force and torque, we can make sure that we design and use objects that are safe and stable. Yes, super important. Okay, so let's dive right on in. Let's say we are looking at a box that has a height of h and a width of w. I'm going to use my physics terminology here. So I'm going to call torque instead of moment, as it's called in engineering. And I am going to leave you with variables, but why I do that is because once you have the understanding of how the equation works and how the variables affect the torque, then you can go in and apply that to whatever object that you're looking at, whether it's a file cabinet or a box you want to jump off of, or maybe a box you want to climb on top of. You can do this before you do that to make sure the object is stable. Okay, so the first thing that we need to do in a stability analysis is to identify the forces that are acting on the box. So right now, even though I haven't added any pushing force, there is the force of gravity acting on the box. And the force of gravity acts at an object's center of mass. Now you see why I did all of those intense calculations to figure out where the center of mass is, because that is really, really crucial to tipping analysis. And also just in general, it's super helpful to be able to do that. So I am going to call this distance d center of mass. In this case, it would actually, so dcm equals w over 2, but I want to keep this as general as possible. In this example, we are assuming a uniform mass distribution, but if you have an object that is weighted, like with sandbags or lead or what have you, or if you have an object that is made of different material where the center of mass is going to change, this will allow you to keep the equation the same, and then you can just actually change that distance depending on the center of mass location. Keep in mind that this is the center of mass location in the x direction, so I actually am going to change this to xcm to help you be consistent. Okay, and so now let's say I have a pushing force that is pushing the box this way. I'm going to call that Fp, and keep in mind forces are vectors, so they have a magnitude or a size as well as a direction. In this case, the force of gravity is pointing downwards, hence why it's the down arrow. It always points towards the center of the earth. And the pushing force is pointing in the x direction. So the next thing to keep in mind is that we have to figure out how these forces are going to cause the box to rotate. So if I apply a pushing force on this box, the box is going to pivot around this point. So you can call this the pivot point. Oh, my jacket's falling off. Okay, so the pushing force is going to cause the box to pivot around this point in this direction. It'll cause the box to rotate in the clockwise direction. So in the clockwise direction, we have Fp. On the other hand, the force of gravity is going to cause the box to rotate around this pivot point in the counterclockwise direction, or CCW. We have the force of gravity. So the next step is to identify the lever arm at which each of these forces are acting. Oh, there's a handy dandy clock. And so in this case, the lever arm of the force of gravity, or the perpendicular direction at which it is acting on the box, is the distance of x center of mass. So I'll just say torque counterclockwise equals Fg times x cm. And for the pushing force, torque clockwise equals Fp times the lever arm at which this force is acting, which is the perpendicular distance, which is going to be the height of the object. So now we have to figure out at what force does the object start to tip over. So that we could call maybe the critical force, and that happens at which so if the object is not moving, then that means that these two torques are equal. If the object is moving, then all of a sudden it's because this pushing force is greater than this gravitational force. So in other words, we could say that the critical force happens at which these two torques are equal, and at a pushing force that is greater than that, then the object will start to tip over. So we set these two equal and we solve for the pushing force. Okay, so in this case we have Fp times height equals Fg, which I'm going to simplify to be mg times x cm. So this box has a mass of m, generic. Okay, so now we just solve for Fp. It's just a little bit of algebra, not so bad. So Fp equals mgxcm divided by h. Yay! That's it. Not so bad, right? Okay, so a couple of things to point out. So the pushing force is directly proportional to the mass of the object as well as the location of the center of mass of the object. What that means is that if we increase the mass of the object by, say, adding sandbags or lead weights or something like that, then we are going to increase the amount of force that's required to tip the box over, aka the heavier the box is, the more stable it is. And likewise, the center of mass location is also going to affect the stability of the object. If we have a larger lever arm for the force of gravity, aka the box is wider, then the pushing force will also have to be greater and our box will be more stable. It is inversely proportional to the height, or you could say it's directly proportional to 1 over h, and what that means is as the height of the object goes up, its stability goes down because the pushing force required decreases. You could also think about that like if you were to push at a lower point on the box, the lever arm for the torque is going to decrease, just like in the seesaw example. So that gives us 3 ways to adjust an object to make it more stable. We can make it heavier, we can increase the center of mass in the x direction by making it wider, or we can decrease the height of the object. Another quick thing that I want to mention is that the center of mass is super critical to the stability of the object. And the reason is because as our object starts to tip over, the force of gravity is still going to be pulling downward from the center of mass. But if we have a lower center of mass, as the box tips over, the lever arm is going to be bigger. Another way to look at that is as the box tips over, a lower center of mass, the lever arm will change less. So try that out by drawing some pictures and finding some right triangles and doing that fun trigonometry stuff. Please let me know if you have any questions about tipping force, torque, or finding the center of mass. That is the first thing that you have to do in any stability analysis, is to determine the location of the center of mass of the object. So if you have a uniform mass distribution, it's fairly straightforward. If you have a non-uniform mass distribution, you'll have to get a little bit more creative and practice your calculus, but you got this. So let me know if you have any questions about this or other math topics. Thanks very much for watching, and we'll see you next time. Bye!